Okay, so today we're doing the lipids lab for Chem 1405, and we need to do a little background first. What are lipids and how do they work, how do they function, and what do we use them for? Lipids are based off of fatty acids. So in organic chemistry, a fatty acid is going to have an acid, carboxylic acid group, followed by a long CH2, long hydrocane tail, just on and on, finally ending in a CH3. This long chain can go out 12 to 18, even 20, but probably 14, 16, those are the most common links that we'll find in the biochemistry of the cell. Of course, I could write that in a shorthand notation. I'll do my acid group here and then just do a line angle formula. And again, it would go out about 12 to 14, 18, 16, somewhere in that range. Okay, that's a fatty acid. Again, they call it that because it's got the acid group over here that can donate that proton, and then this fatty part right here, which is nonpolar. That's nonpolar, and of course this is a polar group. And so you have both polar and nonpolar on the same molecule, which gives them very interesting properties. In fact, in the body, fatty acids named fatty because they come from fat molecules. And a fat molecule looks like this. We've got a glycerol backbone, glycerol, otherwise known as glycerin, same thing, just two different names. Looks like this. I've got to fill in some hydrogens, like that. So it's 3 carbons with an OH, hydroxyl on each carbon. Now if I attach, instead of an OH, see this OH here, right there, if I instead take a fatty acid and plug that in, so I'll take off my H and put my fatty acid going on each one of these, I have a fat molecule. So the fat molecules in our body, in our cells, look like that. A glycerol backbone and 3 fatty acids. And again, these could be different lengths. Even on the same fat molecule, you might have this one longer and this one shorter, right? But that's a fat molecule. It's also an oil molecule. Oil is exactly the same thing as fat. The only difference is, what do these long carbon chains look like? Are they longer? Are they shorter? Do they have double bonds or single bonds? So let's talk about that right now. If I've got a fat molecule here, let's say, and I'm going to just draw it in a kind of a schematic form like this, with its 3 tails coming off here. I'm not giving all the details here. Okay? So it's coming down like that. Typical fat molecule. One of those could interact with another one, of course, like this, because the polar head groups are going to want to line up, and the nonpolar tails are going to want to line up like that. And if they pack very tightly together, then those fat molecules will be a solid, say at room temperature. Of course, you heat it up, it will melt, as you know, but at any given temperature, they're going to be more tended to be a solid if you have good interactions. What happens if, for example, you've got a fat molecule which all of a sudden has a double bond in it like this? Well, let's simplify. Let's just take a fatty acid. It would apply to fat molecules as well. Let's take a fatty acid and we put a double bond in like this. It would pack just fine with other fat molecules, whether they have double bonds or not, because think of the angles involved. These are tetrahedral, so these are 109 degrees, where here this is going to be trigonal planar arrangement with 120 degrees. Very close, right? This is right there, 120 degrees. So as far as packing in next to each other, they're going to still fit very well. That's not a problem. Double bonds, single bonds, it's going to work. However, what if, let's do a third molecule here, I put a cis double bond. So this one I drew trans. What if we did a cis double bond? So then it goes like this. That one's not going to pack so well, right? Because it shoots out this way, and my next molecule would have to be way over here because we got this thing that's not packing because the angle has changed now. So cis double bonds are not going to pack as well as trans double bonds do. Now, why is that important? Let's think about melting points. If you have things that are packing well together, lots of good interactions, that's going to have a high melting point. You're going to have to give it a lot of energy to break all those interactions apart because there's all kinds of them in between here. Here, if you have cis ones in there, they're going to have a lower melting point because I don't have as many interactions, right? I might have some up here, but over here, they don't have the interactions anymore because they don't pack well, right? So if you have cis ones, you're going to have a lower melting point, right? And now, think about it in the body. If you've got these things going through your blood, in your blood in streams going through your veins and arteries, what would you rather have there, solids or liquids? I think pretty clear, you don't want solids that's going to jam things up and you can get plaque formation and that kind of stuff. You want it to be actually liquids, right? Which means cis would be beneficial to have, not trans. And so when you think about like fatty acids and fat molecules in diet and wanting to eat healthy and that kind of stuff, the cis are healthier, the trans are not because they're going to form solids just because of that shape like that. I'll remind you too, when we have a double bond in something, we call that unsaturated, whereas if it's all single bonds, we call that saturated. And we use those terms a lot when we're talking about fats. So saturated is all single bonds, whereas unsaturated, there is at least one or more double bond. And again, whether that double bond is cis or trans is going to affect physical properties such as the melting point. Let's see. Another property of lipids that we should talk about is the idea of emulsification. Soaps and detergents. A soap or a detergent is just a fatty acid where I have put on the end, instead of an OH, I could put something like maybe a sulfate group, SO4 minus like that, or some other charged group to make this end even more polar, more polar. We'll just leave it at that. Why does that help? Well, if this is a soap molecule, this end having a full charge and be very polar, this end is going to like water. It will want to interact with polar water. Where this end over here, being nonpolar, will interact with things like grease and dirt and that kind of stuff. All the things that they don't just wash off with water, right? If you get some really greasy or waxy thing on you, you can't just run your hand under the faucet and it washes away. You need soap, right, to get it away. Why? This part, the nonpolar, is going to interact with that grease, which is nonpolar. This part will interact with the water, and so it kind of acts like an adapter molecule. When you put the soap on first and then you run the water over it, this part's attached to the grease, this part goes with the water, dragging this way along with it, right? And so it's an adapter, and it allows you to wash that grease or dirt away. It's also an emulsification agent in the idea that grease, that's not going to dissolve in water normally, but you put a little soap in, you stir it up, all of a sudden it looks like it dissolves. It's no longer these two layers. Why? It's exactly the same reason. You've got this that's going to interact with the water, this with the grease, and so you can get these two things, like a nonpolar and a polar liquid, to actually mix together if you have an emulsification agent in there. And we say emulsification agent, that's what a soap or a detergent is. Now you can imagine we can make these longer or shorter, we can make double bonds in there or single bonds. We can change the polar head group. So there's a lot of things that we can do to change whether you have a soap or a detergent and how well it works. And so we're going to look at those type of things in this lab as well. Finally, the last part of this lab, we're going to make some hand lotion. Hand lotion is lipids essentially, but we need to get them to dissolve in water. Actually, it's mostly water, but we're going to put these lipids in as well so that it interacts well with our non-polar skin. Right? We have to control the pH. We want it to be not too runny or not too thin. There's quite a few things that go into making a lotion, although the chemistry is fairly simple, just what we talked about here, and the physical properties of it. And so we're going to make hand lotion. We're going to do it the right way. And then we're going to do it two wrong ways. We're going to leave out an ingredient here or there, and based on our test of, well, does it still mix together? Emulsification, right? Does it have a good pH still? Things like that. We'll hopefully be able to determine what that missing ingredient did. And when it's missing, of course, yikes, now it doesn't work so well. Okay? Okay, part A. We have 5 different samples as listed in the manual. We have vegetable oil and olive oil, lard, butter, and coconut oil. And we have just left these in the freezer, and it's just not a normal freezer, actually, minus 80 degree freezer, minus 80 Celsius, that is. So these are incredibly cold. In fact, they're all solids. I don't know, most people have never seen vegetable oil frozen like that, but there you go, it's completely frozen. And actually, now that I've put them out here, I'm going to start our timer. Because now that we've removed them from the super cold freezer and set them out here, they will just slowly melt, right? They will slowly warm up and eventually melt. And actually, to assist that, and so you can see it better, I think what we'll do is we'll go ahead and, if I can get them out of here, maybe. There we go, a little bit messy. I'm going to put it that way so you can see them better. And I'll leave the cups behind it so we remember what's what. So that's the butter. Come on, there we go. That is the vegetable oil. I put the timer on so we can start. I mean, they are warming up right now for sure. That one came out easily. There's your olive oil, all frozen. There's the lard. And here is the coconut oil. What we'll do is we'll just observe those, and when they are about half melted, half frozen, that is, they half liquid, half solid, we'll take our thermometer here and take the probe, and we'll just poke it in to see what temperature it's actually half frozen still and half melted. And that will give us the temperature, the melting temperature of each one of these substances. I mean, for example, we know water, melting temperature is 0. We took ice and did this. When it was half ice and half liquid, we could stick that the probe in and we'd see that it reads 0 degrees Celsius. We have different lipids here. Some of them might be saturated, some of them might be unsaturated. The ones that are unsaturated might have cis bonds or trans bonds in them, and so those properties, some of them might have long tails, some of them might have short tails, right? And so all of those properties will contribute to whatever the melting temperature is. So at this point, we just sit and wait and watch them, and when one of them gets to halfway, we'll measure its temperature. Okay, we are up to 8 minutes and 21 seconds here, and so I just want to update where we're at. Coconut oil, it's still very solid, very hard. It's cracking a little bit, that's okay. The lard, same thing. Olive oil, same thing. The vegetable oil, now this one's getting mushy. This one's definitely starting to melt a little bit around the edges, so you can see it at, maybe you can see it at the bottom, it's starting to leak out a little bit. So this one's starting to melt. Butter, still very hard. All right, so this one is the first one that's showing signs of melting. It's not half-half yet, so we won't measure the temperature, but that one's going first so far. All right, we'll cut back in as that one melts a little more. Okay, we're up to 15 minutes now. Let's see where each sample is. The coconut oil is still very solid. The lard, it's getting a little bit of a squishy feel, just a little bit, but it's still pretty solid. Olive oil, that's definitely getting soft around the edges, so it's getting on its way. The vegetable oil is half-half, so we're going to measure the temperature of that in just a second. The butter is actually pretty hard still. All right, so with our thermometer, we'll take the, can you see that okay on the camera, hopefully? we'll take the probe and we'll put that in here. Right now it's just measuring room temperature, which is 22.3 Celsius. We'll push the probe down into this and we'll see what temperature we're at. It's about -10. So apparently vegetable oil will have a melting point of -10 degrees Celsius. Okay, so we'll cut again and we'll wait for the next one to get a little mushier and maybe half melted, and we'll come back with the video then. Okay, we're up to 27 minutes now on the timer. This is still solid. Coconut oil, lard is starting. I don't know if you can see that. It's starting to melt right in the middle, interestingly, not around the edges. So that's kind of odd, but it's still solid for the most part. Olive oil is getting really squishy. We got a lot of melting excuse me, around the edges. You can see the liquid down there, but it's mostly solid still. So this one's close. Our vegetable oil is completely melted now. It's just pure oil now, liquid. Our butter is pretty solid. So what I'm going to do is we'll let this one keep going at room temperature, but to speed things up here, we're going to take the three that are pretty solid still and put them in these water baths back here to give them a little extra heat and get them to melt a little faster. And so I'm going to move this here so I remember which one is which. Actually, maybe I'll do it over here. This back one here will be the butter. So I'm just going to splash a little bit. That's okay. The lard we'll put right in front of the butter like that. And so, and the coconut oil we'll put in the front spot here, like here. There we go. And so that will just get them to warm up a little faster. We've got them on the hot plate. Hopefully not too fast. I'll just keep this on maybe about a 2. And so we're watching for this one to go about half-half, and now these three as well. And I have to just watch very closely. And these might go a little quicker now that they've got that heat source like that. I don't know if you can see it. Okay, maybe we bring the camera a little closer so we can look down into there and see which ones are which. And actually, you can see if you get down in here, the coconut oil is melting pretty quickly now in the hot water. I might want to take it off and just go by hand. I don't know. It's up to you. There we go. That works. Okay. And so it's getting there. Actually, that coconut oil is just about half-half now. Unfortunately, it also spilled, and so it's in the water, but being that it's non-polar, it's going to flow to the top, and so I'm just going to put the probe right there at the very top here, and we'll see the temperature. Looks like about 52-ish. We'll put it down right on the solid. Let's see what that shows. Yeah, about the same. So we're going to say it's about 50 or 52 for the coconut oil. The butter back here is doing pretty good. It's not quite halfway, but very close. So we'll let that go about halfway. The coconut oil, because it did completely spill in the water like that, I mean, we measured 52, but I'm not convinced that's a terribly accurate reading for this experiment. We'll record that all the same. that butter looks about halfway melted to me right now, so we're going to go ahead and test the butter. Put that in here. There we go. And the butter seems to be at about 38 degrees. So we'll call 38 for butter. The lard is almost at the halfway point. Give it a little bit longer here at the outer temperature. Alright, that's just about halfway. So lard looks like we've got, about 50, maybe. Actually, I take that back. It's more like, it also got the water spilled in on it as well. So more like about 36, I'm going to say. 36 for the lard. And finally, let's go back down here to the tabletop, bench top. The olive oil, it is just about halfway, very soft. So we're going to go ahead and measure that at this point as well. Stick this right into right next to it where it's kind of right at the transition. And that's about 5.3 or 5.1, somewhere in that range for the olive oil. All right, so clearly we have different melting points based on, again, the structure, the type of lipids that each one has. Part B. Here we're going to take those same 5 samples, the different lipids, and test them for 2 things. We're going to test the ability to be emulsified using either a powdered laundry detergent over here or some hand soap. We'll make some solutions of that, then we'll put our samples in there, we'll see which ones actually emulsify it. That is to say, you're going to be looking for, does it mix well, and does it stay mixed well over time. The second thing we've been looking for in this part is whether there are saturated or unsaturated samples. We can do that using the potassium permanganate. If we add that potassium permanganate dropwise, and you see a pink color or a clear solution, that will indicate whether it's saturated or not. But we'll talk about that more when we get to that. So first of all, following the protocol of the book, it says make 2 solutions, 100 milliliters of water plus either some soap or some detergent. So let's grab our hand soap here. We're going to have to weigh some out, and so I'm just going to scrape some off here. We're going to need about 1 gram of it. I'm not sure how much soap that will look like. So I'm going to just go ahead and shred up a bit of it here. I think that'll probably be enough to make up 1 gram or so. We'll find out. Just going to get it into a pile here. Alright, so there's our normal hand soap, and again we've got some detergent. So we need 100 milliliters of water in each of our beakers. This is DI water that I grabbed ahead of time and put in the beaker here so I'd have it on hand. Okay, there we go. That's 100 milliliters. Put that in the first beaker. And same thing for the second beaker. Okay, in our first one we need the 1 gram of soap that we just shaved. So let's do our balance here. Put a weigh boat in. We'll tear that. And let's put a little soap on here. Get 1 gram of it. That's 1/2 gram. Again, we're not doing really quantitative work here, so I'm not going to worry about hitting it exactly, but I want to get close if possible. Like 9.5, 9.6, maybe just a little bit more. There we go. Hey, that's pretty good. 1.007 grams. So here's our soap solution. We'll go ahead and take that and add it to the 100 milliliters of water. Let that dissolve. Okay, solution one, and we'll stir that up. I've got a stirring rod here. It's probably not going to completely dissolve, but a lot of it will anyway, and that's all we need. We want a saturated solution of the soap. A little bit of solid is remaining, that's okay, it just proves that it's saturated. Okay. And I'll just put that down here. For beaker B here, we're going to do the same thing, except we're going to use the detergent. And so, let's get another weigh boat. I spilled a little bit of soap in that one. I carried it over, we'll get a clean one here. Okay. Tear that, and we'll get the laundry detergent. Laundry detergents, of course, don't set up like soaps do, but they're still emulsifying agents. That's why you could use them in washing machines and dishwashers. You wouldn't want a bunch of bubbles coming out of your dishwasher, right? And if you put normal hand soap in it, that's exactly what will happen, where detergents don't tend to bubble up like that, but they're still emulsifying agents. The detergent, according to the protocol, we don't need a gram, we just need a half of a gram. So I'm sneaking up on it here. Almost got it. There we go. We've got 0.506 grams of the detergent. Do that in the second beaker. And again, we'll stir that up. And you can see the difference, again, detergents don't bubble and set up like the soaps do. And that's very obvious, I think, when comparing these two solutions. They do a little bit, but nothing like this guy did. All right, very good. We've got our two solutions now. We've got, let's bring the camera closer, I think, maybe, and I'm going to bring those over here. So we've got our 5 test tubes, one for each of our samples. Again, we've got the vegetable, olive, butter, lard, and coconut oil. We're going to go ahead and put back here in the S ones, this for soap, or the D for detergent, we'll put 5 milliliters of those soap or detergent solutions that we just made into each test tube. Here's the soap one. I previously put 5 milliliters into a test tube just to see what kind of volume that is. Again, it doesn't have to be perfect. And so you see it's about halfway filled or so. And so using that as a gauge, I'm just going to about half fill each one of these test tubes up. I think my hand's probably in your way. You've seen what I'm doing here. But, I mean, I'm just pouring some stuff over, so there we go. That's about half fill, maybe a little more. It's okay. For what we're doing, that's what we need. Soap into all 5 of these test tubes. And again, the soap and the detergent are the emulsifying agents. They're the adapter molecules, if you will, that will allow the polar and the nonpolar solutions to mix where they normally wouldn't. All right, so there's our soap test tubes back here in the back of my rack, and my detergent solution we'll put in the front test tubes. Same idea. We'll go about halfway up or so, 5 milliliters or so in each test tube. Okay. Two different types of emulsifying agents, right? Step 3, it says now, using the melted samples from before, and I'll bring those over here, put 5 or 6 drops of each sample into each test tube with soap solution and a test tube with detergent solution. Shake each one vigorously. So we'll add each sample, like with the vegetable oil, we'll put 5 drops in here and we'll put 5 drops in here. And then we'll do the same thing with the olive oil in the second test tubes all the way through, and we'll see how they mix. So our first sample is the vegetable oil. Let me just walk over here and get those two. Actually, I can bring both of these at the same time just to save a trip. All right, so the first one we had here was the vegetable oil. We'll draw some up and put 5 drops back here. 5 to 6, they said. So 1, 2, 3, 4, 5. I'll go for 6. In here, 1, 2, 3, 4, 5, 6. I'm tempted to go a little more because I want you to be able to see the different layers in this. And so I'm going to modify the protocol here, make a note of that. We're going to go for the full, maybe 10 drops. So 7, 8, 9, 10. 7, 8, 9, 10. Just because I want that to be fairly clear what we've done. And what I'm talking about here is if I hold this test tube up, you can see hopefully the top layer, the vegetable oil, and the top of that test tube, and then the solution down below, the aqueous solution below. You see that layering because, again, polar and nonpolar. Now, I know we did a soap solution that should be emulsifying agent, but we haven't mixed it. We haven't shaken it yet, and so we haven't allowed them to interact. The same thing here in the detergent solution. We have the aqueous down below, and hopefully you can see that layer, that top layer of the vegetable oil. All right, let's go ahead and do all the other samples as well. So the second sample is going to be olive oil. And we'll do 10 drops of olive oil in each. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay. Move those out of the way. Get the next samples. The next one is butter. This is the ones that were in the water, and so I'm going to try to carefully carry it over so that we don't get it mixed too much with the water. Although if it does mix with the water, again, it should be floating on top of the sample. And so if I just dip in near the top, I should get just the melted sample without water, which is what I've done. I've just sucked it right off the very top. All right, so here we go. The butter. Oops, I got a lot of air in there. Let me get that air out. All right, there you go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Next will be our lard sample. Melted lard. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. And lastly, coconut oil. This is the one that actually spilled the most, so. And with the melted coconut oil, it looks totally clear, just like the water. And so I'm just going to kind of take it on faith that that top layer here is the coconut oil. And actually, it's true. If you look very closely, you can see there is a top layer on the top, and then the water's down below. So as long as I stay just in that top layer, I should get the coconut oil. So I just need to be really careful here as I go down and get it just off the top layer. All right, I think I succeeded. 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little drippy. 1, 2, 3, 4, 5, 6. Got some air bubbles in there. 7, 8, 9, 10. All right, I think we got it. And again, on each one of these, like the butter one is very clear. You got the 2 layers because it's actually got that different color to it. Same thing with the olive oil. It's colored nicely so you can see the 2 layers. And these are a little harder, but you can still see it. And again, there's that coconut oil. You've got the layer on the top. And the lard. Actually, the lard's actually beginning to turn solid in the cooler temperature already right there. Okay. So we've got our drops in, each different, the soap and the detergent. It says shake each test tube vigorously. So let's go ahead and put a rubber stopper in each one, and we'll shake them up. Okay, here we go. Vegetable oil in the soap. Again, we start with that layer. We'll mix it together. Of course, we got a lot of bubbles forming and that kind of stuff because it's the soap. Looks like that initially. It is settling out. The key thing here is if you go down to the liquids, I know we got all the bubbles up here, but we're not seeing the layer anymore now. We actually got those 2 things too mixed together, and again, that's the whole point of an emulsification. Here we go with the olive oil in the soap. We'll start with that. Shake it up vigorously. And there we go in the emulsified version. Of course, we'll let them settle out here in the bottom. We'll come in closer with the camera once we do that. Here's the butter. Got it mixed together. The lard. Like that. And the coconut oil. Again, we got the layer there initially. All right, now we'll do the same thing with the samples that are in detergent. You can see again the layer. Here's the vegetable oil. With the detergent, you're not getting as much sudding, not as much bubbles, but you still get, hopefully, emulsification of the sample. Olive oil. That. Butter. The lard. Again, the lard is actually starting to turn solid, so I'm going to give it a little more shaking to hopefully get it to interact with either the soap or the detergent, but that may prove to be difficult. And finally, the coconut oil. Okay. So we've got them shaken up. I think maybe if we can get in nice and close with the camera here, and this is now they've been setting here for a couple minutes perhaps, for the ones at least in the back. I'll tell you what, let me move this out of the way. I'm going to move these over here so hopefully we can see them all at the same time. A little bit easier to see the camera. Or I can even put them up there, I suppose. But, is that okay? Can you get it on the camera? All right, let's just take a quick look at them. We know that they all seem to emulsify okay when we first shook them up. And one of the things we want to look for is to see, do they stay emulsified though? Sometimes you can shake them up, the initial emulsification works, but then you let them sit, they can still settle out a little bit. The instructions in the protocol say to carefully observe each solution. In particular, note whether the sample quickly forms an emulsion, which I think they all did actually. And number 2, do the samples remain mixed after a few minutes or do they separate? And so again, we'll see if you could observe that as they are sitting there. Do they remain emulsified or not? Kind of lift each one up so you can maybe see it a little better. That's the vegetable oil with the soap, olive oil with the soap, butter with the soap, lard with the soap, and you can see the lard, again, we've got that solid forming, so that's a good observation there, and the coconut oil with the soap. And in front we've got the detergent, again, vegetable oil, olive oil, butter, the lard with the solids, and the coconut oil. And so the soaps and the detergents will work more or less with the various samples, just depending on how well those interactions are between the molecules. Okay, next, step 5, it says potassium permanganate, which we've got here. Potassium permanganate will allow detection of unsaturation, so again, double bonds. It says if unsaturation is present, the pink will lose its color. So if you have double bonds, this pink solution, now you can't see it's pink here, but when we take it out, we draw some up in the dropper. Purple, it's so pink it's purple actually. All right, but when you put a couple drops in, it's going to look pink because it'll be diluted, okay? So that pinkish color that you're seeing there will lose its color if there are double bonds present. Okay? So what we're supposed to do here is first add 1 drop at a time, shaking between it until it stays pink. These are the number of drops. Oh, hang on. I need to use this guy first with some detergent, and I never poured detergent into it. That's okay, we've got it right here. This is going to be our negative control in the sense that we have detergent in here. We want to just see how to, with no sample, what does this actually look like? Okay, and so we're supposed to add this now, drop by drop, add it until the solution stays pink. So let's go ahead, we'll do 1 drop. You can see what that looks like. Shake it up, and it's got a color, but it's not pinkish. So here what we're seeing is just kind of a dilution. There may be some double bonds even in that detergent. I don't know. 2 drops. Well, that's kind of pink. I don't know, would I call that pink? Or let's try 3 drops and see what happens with 3. 3 drops. Just a little bit darker of the same. So 2 to 3 drops, it seems like, is what, if there are any double bonds in that detergent, now it's reacted. If I add more, you see now it's going pink because there's no other double bonds for it to react with. So the idea is we're going to test all these samples the same way. The first 2 drops will, if there's double bonds, it would react with in the soap or the detergent. Beyond that, if it stays pink, or I'm sorry, if it stays clear, that means there's double bonds in the sample as well. Okay. First sample is the vegetable oil with the soap. Now, of course, I want it to be emulsified. It has separated out, so I'm going to shake that back up, get it mixed up, so then that would allow the
potassium permanganate to react as well. So let's do 2 drops, 1, 2. And shake that up initially. Okay, and it is clear because there were double bonds in there somewhere, and again, it could have been with the soap. But now if we add 2 more drops, if there's anything with the sample, that's what it should be reacting with now. And you see it does not stay pink, it actually goes clear. I won't give away what that means, but you should be able to think that through. Again, this will go clear in the presence of double bonds. All right, let's do the soap with the olive oil. Testing the olive oil. I'm just going to go right for the 4. 1, 2, 3, 4. We'll shake that up, and there's that initial pink. And there we go. It is no longer pink. Butter with the soap. 1, 2, 3, 4. Lard with soap. And coconut oil with soap. All right, we'll try the same thing with the detergents. Four drops. That was the vegetable oil. There's the olive oil. There's the butter. Here's the lard. And finally the coconut oil. So, here's your results. I'll go ahead and zoom in on that. I have a feeling that the soap, which we did not do a negative control with, the soap might have more double bonds than the detergent has, based on those. But because they all pretty much lost their pink back here, so I'm thinking the soap actually reacted with it. But here you've got a clear difference between some that did not lose their pink so much and other ones that did. And so I think probably the detergent ones are a little more accurate in this example. But you should take all that data down and think it through, come to your own conclusions. Okay, part C, lotion. We get to make lotion, which again is a mixture of water and fatty acids, fat molecule, pH buffers to control the pH, emulsification agents, so mixture of everything we've been talking about. We're going to go ahead and make the lotion. The protocol says to make the lotion first and then go back and repeat it leaving or omitting one of the ingredients and then do it again. So what we're going to do here is just all 3 times at once. We'll have 3 beakers going. One of them will be the normal lotion, and the second one we'll leave out one of the ingredients, and the third one we'll leave out a different ingredient. So that way we can just do it in one shot here. All right, so step 1. It says place the following non-polar ingredients into our first beaker. 3 grams of stearic acid. All right, so I need to do this 3 times. So in triplicate, I want 3 grams. Get a sense of how much that is. It's very fluffy solid, very light. Even though I've got a lot of in these scoops, it's not adding that much to the weight, as you can see. Stearic acid. Dr. Shin, what is stearic acid? 18 carbons, if I remember correctly?
Yes.
I think so.
Yeah.
I always get these names mixed up because you've got palmitic acid, you've got stearic acid.
This is a citrate, right?
What's that?
This is a citrate.
It's, I believe,
Stearic, yeah.
saturated,
Mhm.
18 carbons,
18
I think, is
carbons,
what
yeah.
stearic is, right? So there we go, 3.1 grams. That is close enough for lotion. So there's my first batch. We'll do it for the other 2 beakers. Whoops, it did not tear, and I got ahead of myself there. So let's allow it to 0. Try that again. I think maybe I bunched, I think I hit it and it was touching the wall. There we go. Now that's looking good. Okay. So I want 3 grams of the stuff. There we go. Beaker number 2. And one more time. Grams. All right, beautiful. Next, 1 gram of cetyl alcohol. This surprises people. Cetyl alcohol, they think alcohol is liquid, but no, not all of them, right? Here we actually have a solid. It is an alcohol. We want 1 gram of cetyl alcohol in each beaker. This is kind of a flaky sort of a solid. Again, not very dense. So visually it looks like there's a lot on there, but there's a lot of air, I guess, mixed in probably with those crystals. It's very low density material. All right, there we go. 1 gram of cetyl alcohol into beaker 1. Beaker 2. Pretty close, a little bit more. There we go. And beaker 3. Now it just dawned on me, I'm supposed to be leaving out some component. I hope one of them wasn't either the cetyl alcohol or the stearic acid that I was supposed to be leaving out. Let's see. One of them was the stearic acid, and the second one repeated without the ethanol. So, silly me, in one of these I was not supposed to put the stearic acid, and that was the last one. So that's okay, I'm just going to dump this out into the waste. All right, the stearic acid was the first thing. We omitted that from the third one, but we do need acetyl alcohol, so 1 gram of that still. I'm glad I thought of that before I went too much farther. Okay, here we go. So the third lotion does not have that stearic acid, but it does have acetyl alcohol. So that will tell us what the stearic acid is doing when we see what's wrong with our lotion from that third beaker. Right? Okay, the third great ingredient, 2 grams of lanolin, also known as wool wax. So liquid lanolin looks like that. It's a very thick, viscous sort of a liquid. And we're supposed to put 2 grams of this in each one. 2 grams. Kind of weird weighing out a liquid. But I'm just going to drizzle that in. Actually, let me get one of the smaller weigh boats. I think that might work better. Great. Thank you. For the liquid, I think that, and it's got a little pour spout. I think that might work a little bit better. So we'll put that in. Okay. Tear that. And 2 grams. Okay, there we go. And 2 grams, looks like about that much. And all of these are non-polar ingredients. Let me see if I can just scrape that out maybe a little bit. Okay. One more drop on. There we go. That's pretty close to 2 grams anyway. Probably a little less, but let's get the second one. Lanolin. A little more than 2 grams, but it's not all going to come out of here anyway, so I'm happy with that. A wax, by the way, this is known as wool wax, lanolin. A wax is similar to oils and fats. It's not a triacyl. What a wax looks like molecularly is a long hydrocarbon chain with an ester bond in the middle of it. And when I say an ester bond is simply a C double bond O with another oxygen, similar to a carboxylic acid, except instead of ending with a proton, it goes on to another acyl chain. So you've got waxes in here that are probably a grand total of 40 to 60 carbons long. And so that's what makes these so viscous, kind of like a thick oil. It doesn't want to porous, right? It's very thick and gooey. That's because you've got these very long hydrocarbons in there with lots of interaction between them. Makes for that kind of a liquid. Okay, there we go. So we've got our non-polar ingredients, except this one, of course, is missing the stearic acid. Okay. Next, we're going to go over here. We've got 3 beakers. Again, we're going to mix together the other ingredients, which are mostly polar. All of them are polar, in fact. So we've got our non-polar ingredients in the first set. In this set, we need, first of all, 2 milliliters of glycerin. So here's 2 glycerin. Glycerin is another one of these very thick, gooey sort of liquids. And I can just use this gauge on here to measure out 2 milliliters. One glycerol or glycerin, remember, is the backbone of fatty acids, so we already talked a little bit about that. It's 3 carbons with a hydroxy on each carbon. 2. Okay, so here, oh, I got a lot of air in that one. Let me try again. Don't want to be measuring air. Okay, 1 milliliter. Two. Oops, I got one more beaker, don't I? One. Two. Okay. There's my glycerin. The second one, 50 milliliters of water. Like we said, lotion has a whole lot of water in it. You're buying a bunch of water essentially when you go to the store. There's extra little components kind of added to it. Alright. Look at all that water. Clearly the bulk of it is water, right? That's okay, the bulk of you and I are water as well. What are we, 70, 80% water or something like that? Alright. And you see it mixed very nicely together because again they're both polar. So we would expect that. You see it, 50 milliliters here of water. And as you can see, I'm not being super careful with my measurement. But again, we're not doing anything quantitative on this. This is called qualitative chemistry, where as long as you're pretty close, it should work, and you're looking for what properties are. I'm not looking to measure carefully, and so that is good enough what I just did there. So approximately 50 milliliters in each one. And last 2 grams, I'm sorry, I read the wrong one, 1 milliliter of triethanolamine. Triethanolamine. 1 milliliter in each one. Except, this is one that we're going to omit. We're going to omit that in the second test tube. The second lotion will not have triethanolamine. So, this is another one of these very thick liquids. There's one. The second one, we'll skip that. Two. Okay. All right, so now we've got our non-polar ingredients over here, polar ingredients with the appropriate ingredient missing in lotions number 2 and 3. Okay, step 3, place both beakers into the water bath on a hot plate and heat it until they're completely melted. All right, so these guys are clearly not melted. And we've got a water bath over here. Let's go ahead and, I want them to tip over. We might have to remove some of that water from here. Yeah, they're starting to float a little bit too much for me. So before I do that, let me just take a beaker and remove some of the water. Sorry, looking for a beaker. Got a little bit too much water in our water bath. Our beakers are going to go floating away. And worse yet, spill. And don't want that. All right, let's see if that helps. That's pretty good. Okay. And, well, lotions always smell nice, but it has nothing to do with the action of the lotion itself, right? That nice smell that lotions have is simply additive, so that they can sell their product better. And so what we have is some essential oils. We've got some jasmine oil here, some chamomile, and some eucalyptus. And so we'll throw some of those essential oils, just a drop is probably fine, and make our lotion smell nicely. All right, look at that. That one's totally melted. I'm going to turn this off in fact. And hear the beakers rattling around. That one's melted, and so is that one. So we're all set. That didn't take very long at all. Now we can combine them together. All right, and so step 4 says combine the beakers by pouring the water and the glycerin mixture, that's these guys, into these guys. Okay, so let's go ahead and take our melted ones out. There's beaker 1, beaker 2, and beaker 3. And we'll go ahead and add 1 to 1 and 2 to 2 and 3 to 3 of the polar ones. So, that in here. Goes in here. And that goes there. All right, now we just mix them up here a little bit. So, beaker 1 is the one where we did it correctly, and because it's a little warm, it's runny, but as it cools off, it will thicken. So there we go. Number 2, this is the one that we left out the ethanolamine. And as you can see, that's not looking so good as far as a lotion, that's for sure. And number 3 is the one that we left out, the stearic acid. And again, not looking so good. So all components are definitely going to be necessary. Let's go ahead and add a little fragrance to each one just for the kick. Well, the first one should be just fine. I'm going to have myself some nice hand lotion after this. All right, I'm going to go ahead and add just a drop of eucalyptus. I like the smell of eucalyptus. Oops, I think 2 went in, that's okay. It doesn't take much of these. We'll put some jasmine in the second one. And some chamomile in the third one. Not that they're going to be good lotions anyway, but all right. Stir that up. And it says here in step 5 to test the pH of the lotions. So we'll go ahead and we'll test the pH in a second here. And then also it says record the data, record additional observations such as the smoothness and the appearance. And so as we look at these, keep that in mind. You're supposed to be recording. What do these things look like as far as lotions? And did they work? Did they not work? All that kind of thing. So let me just stir this up a little more and then we'll do the pH here. Back them up so we can put the pH paper in front of it. Thank you. Alright, so we need 3 pH papers. There's that one. Not push it in too much, and when you have gloves on, sometimes it's hard to grab. There we go. You got it? Okay. So while my stirring rod's in this one, let's go ahead and test the pH. So stir it up, you have some on it, and then you add it there. So we got that color here. And need some water just to rinse this off with. Okay. Let's do the second one, pH. Very different results, right? Rinse my stirring rod off, and then the actual good lotion. pH of that one. Okay, let's match those colors up to the scale. So the good lotion, and you can match up the color to the right pH. Remember, pH of 7 is neutral. If I go less than 7, I'm sorry, this is just one. Oh no, that's good. Got the numbers. Let me take this out so it's easier to see. There we go. We got the numbers that are less than 7, which are acids, and the numbers that are greater than 7 would be bases. 7 itself is neutral. Our body chemistry is about 7.4, 7.2 to 7.4, right in that range. All right, here's the one that is missing the triethanolamine. And you see a very different pH on that one. Much more of an orangey type color. And then the third one, the one that was missing the stearic acid. Looks like that. So by looking at those pHs, it helps to determine what the function of each one of those was. Next, again, let's look at just the other properties of it. Does it look like good lotion? Could you put it on your hand? So this one, how would you describe that? I don't know. Is it dissolved well together? Is it well emulsified or not? What's the appearance of it? How thick is it? Right? It's very runny, actually. All of those types of observations are what you should be writing down and recording as your data. The second one, remember, that's the one that was missing the stearic acid. The second one was missing the triethanolamine. Again, what does it look like? I can tell you right now, it's more gritty. I can actually feel it. You can see it on the stirring rod. It actually sticks to it like that. So it looks like that. Very clumpy sort of looking. Very runny. I don't think I could spread it on my hand very well. I don't think that would make a good lotion. Just wipe that off. And then their actual lotion. Actually looks pretty good, right? Very smooth. Actually, if I stirred it up, I could get it probably even more smooth if I really wanted to work it, but it looks pretty good. Actually, just like that. Smells like eucalyptus. Well, that's why I put it in. So, you know what? This is the only one that I think I'm actually brave enough to actually go ahead and actually use it as lotion. Absorb pretty nicely into the skin. Now I have nice smelling hands as well. I'd say we had a successful lotion there. Okay, I think we're done.